Hi, or здравствуйте. Welcome to my talk. So I'm Joe. I like computers, and I once had a blog called timetobleed.com where I blogged about lots of like low-level programming stuff and infrastructure stuff. So there's a lot of blog posts on my blog that are similar to this talk if you're interested in this sort of thing. On Twitter, I'm just Joe Domato if you want to follow me. I'm the founder and CEO of a company called Package Cloud. We make it easy for people to create and manage repositories of Java packages, RPM packages, Debian packages, Python stuff. It's awesome. You should check us out. If you want to follow along, the slides are online. If you go to this URL, you get the slides right now. It's just bit.ly/impossible-infra. And here's another link too. I wrote a really long 150-page blog post about the entire Linux networking stack, explaining everything for monitoring and tuning the entire Linux networking stack. So if you're interested in Linux stuff, you might want to check this out. Anyway, on to the talk. Infrastructure as code might be impossible because nothing works. That's sort of the idea behind my talk. And to begin, I think it makes sense to start with re-examining what code actually is and what we mean when we say code. And then we can relate that back to infrastructure code, and then we can talk about why nothing works. So what is code? Well, in the simplest possible terms, your code makes your computer do stuff in really small steps, right? And each step that your computer takes while it's executing code is made up of a keyword in a programming language and a bunch of other stuff. And so the keywords of your programming language let you use your computer, right? And different programming languages have different trade-offs. Some languages are really difficult, and people recognize them as being difficult. And so some examples of languages that are difficult that people know are difficult are languages like assembly, C, C++, and so on. And because people know that these languages are difficult to use, they're treated in a specific way where you know that if you're writing C code or C++ code or assembly code, you need to be really, really careful. And there's a certain set of programming techniques that people use when they use languages like this. And what I would say is that if you're using a language like this, you know, or you should know anyway, that you need to use languages like this defensively. And what I mean by defensively is that you need to use them in such a way that you're protecting yourself in case anything goes wrong, because they're inherently difficult and dangerous languages to use. And that brings me to my first story of the talk that I want to give today about seeing sort of how people use programming languages in the wild to prevent like infrastructure things from going wrong. So this story involves two main characters. There's the Opteron Revision E processor and MySQL. So the Opteron Revision E processor was sort of a standard AMD processor, very similar to every other AMD processor out there. And it has, the similar set of x86 instructions. But what's special about the Opteron Revision E processor is that it has a set of instructions that are supposed to be atomic instructions, right? So these are instructions that system programmers use to build things like mutexes, semaphores, readers, writers, locks, and so on. And the guarantee with these instructions is that when you use them, they're guaranteed to execute atomically and only modify a specific piece of memory one instruction at a time. And people use these instructions to build higher level synchronization primitives like mutexes. Well, it turns out that on the Revision E processor in the Opteron line, atomic instructions are not actually atomic. And so what that means is that if you were trying to use a mutex in any programming language that was operating on an Opteron Revision E processor, your mutexes wouldn't actually work. They wouldn't be atomic. So you wouldn't be able to guarantee that a piece of code was only being executed by one thread. And so MySQL fits into this picture because MySQL is written in sort of C, C++, right? And MySQL itself was able to detect that the mutexes it was using from the system libraries were not functioning properly. And the reason why MySQL was able to do this is because MySQL was written in a particular way, that it was written very, very carefully with a lot of thought and a lot of engineering investment to build a reliable piece of software. And so MySQL, instead of exploding when the mutexes weren't actually working properly, was able to raise a warning and say, hey, these mutexes aren't working the way they're supposed to. There's probably a hardware bug here. And then folks at MySQL were able to use that to figure out that, hey, there's actually a problem with this processor line, and then Intel was able to set up an errata, and then they were able to correct this hardware problem in a future processor. And I think this is an interesting story because it shows that if you write code really carefully in languages like C and C++, you can actually protect yourself against things being wrong, things like the actual processor on your computer not working properly. So I don't know, I think it's just like sort of an interesting anecdote to show that like when you use like sort of really low-level programming languages, you have a lot of control over what happens on your computer to the extent that you can protect yourself against your computer actually not even working. And I want to contrast that with programming languages that people think are easy, but in my opinion are actually even harder than programming languages like C and C++ and assembly. And so some languages that people think are easy but are actually really hard are languages like Ruby, Perl, Bash, Python. Like, these languages are basically impossible, but people think they're really, really easy, right? And I think that this makes them incredibly dangerous programming languages. As an aside, like unrelated, like I think that in order to write like good Ruby or Python code, you need to be an expert in C, but that's like a different talk that I'm not giving today, and that talk's called High-Level Languages Don't Exist. Anyway, the reason why these languages like Ruby and Python and stuff are impossible languages is because you can't actually use them defensively enough, even if you wanted to, right? So like if you're the folks writing MySQL or some other program in C or C++, you can build your code in such a way to prevent critical failures from happening, even if your hardware fails. But if you're writing code in a language like Ruby or Python or whatever, you literally can't do that, right? Like if there's something wrong with the language runtime and the language runtime itself segfaults, there's nothing you can do, right? You're just out of luck. And I have two interesting stories about that, right? So to sort of relate back to the previous story I was telling you about MySQL, in the case of Ruby, right? I don't know if any of you ever run Ruby in production. Perhaps you've seen the Ruby VM. Occasionally it'll crash or segfault. And the reason why that happens is actually sort of a complicated mix of reasons. But one of the most popular reasons that happens is because the Ruby garbage collector is unable to determine exactly when an object is still in use or not in use anymore. And occasionally the Ruby garbage collector will free and delete an object that you're still expecting to use later on in your program. And when you do that, that ends up in the Ruby VM exploding and crashing, and then your program dies and you serve a 500 to a user or whatever. And there's nothing you can do about that, right? Like, unless you disable the garbage collector, you literally can't write any Ruby code to protect against the virtual machine from exploding. And similarly, when it comes to things like the threading implementation in the Ruby VM, in Ruby 1.8 there was this really crazy performance problem that I'm going to talk about later, where when you're running /configure to configure your source code prior to building and installing Ruby, the configure script actually had a bug in it where it would select the wrong version of a system call that would add a huge performance penalty to actually using threading in the Ruby VM. And I'm going to talk a little about this later, but in that case, right, there's also like literally nothing you can do because you don't have control over the Ruby VM, right? If you're just a Ruby program running, there's nothing you can do to say, hey, I want to use a different threading implementation, unless you can actually go through and rebuild the Ruby VM and redeploy it. And the point I'm trying to make, right, is that like higher level languages like Ruby are promising you that like you can do all this cool stuff, but like underneath the covers of it, there's like all these like really, really difficult, weird things happening, right? And these bugs, like the ones I just mentioned, are really, really insidious because they're really difficult bugs to debug, they're difficult bugs to understand, and they're really, really difficult bugs to fix. Like, it took me a really, really long time to dig out and understand this bug with the Ruby garbage collector, that it would occasionally free objects that were actually still in use. And sort of the point behind all this, right, is that in other words, like the code that you're writing every day, it does things that you don't understand. It does things outside of your frame of reference. And the reason why your code does things outside of your frame of reference is because when you write code in a high-level language, you're invoking thousands of lines of code underneath you in system libraries, in your kernel, in everything underneath you. And there's no way you can read every single line of code all the way down. There's just literally millions of lines of code. It would be impossible. So if you agree that it's difficult or impossible to read hundreds of thousands of lines of code all the way down, starting at your Ruby code and your Ruby VM and your system libraries and your kernel, then I would also say that infrastructure code is similar, right? Infrastructure code makes your computer do really complicated stuff in small incremental steps using a set of keywords, except that for infrastructure code, your keywords are really, really high level. So I'll give you an example. This is some infrastructure code for Chef, right? You want to install a package, right, in this case, blah package at a particular version. When this executes, what's actually happening? Well, what's actually happening is that Chef is spinning up a few different programs. Each of those programs are pulling in, potentially thousands of lines of code themselves or inside their own internal libraries, right, to figure out how to install this package for you without you having to do anything. And similarly, this code is written in Ruby, right? So you're also pulling in all the Ruby VM code, all the all the potential libraries that Chef has to pull in to run this code. So you're talking about literally potentially hundreds of thousands of lines of code are running just because you're trying to install a package with this simple piece of code. And it's not just Chef, right? It's also things like Puppet, right? This is an example from Puppet. You're trying to install a particular package, right? Puppet code is also sort of like this weird Ruby / like C++ thing. And this is potentially pulling in like thousands of lines of code in Puppet, thousands of lines of code in their system libraries, so on and so forth, all the way down. So we're talking about hundreds of thousands of lines of code that are running that you've probably never read or don't know anything about. And so, with that in mind, right, like what if I told you that, infrastructure code operates outside of your reference frame as well? So it's not just Ruby code in general that's hard to understand, right? It's also your infrastructure code which is hard to understand. And what I mean is that, right, like unless you've read every single line all the way down, like unless you've read every single line of Chef, or every single line of Puppet, every single line of your Ruby VM, every single line of your system libraries, and every single line of your operating system, you don't actually know what's happening. And you've definitely never done that because there's just too many lines of code. No human being could do this without going crazy. So if you agree with that, which hopefully you do, because I think this is true, here's a bunch of like really interesting stories about infrastructure code failing in like really spectacular ways that sort of relate to this idea that there's too many things happening. So here's a few things that probably you didn't know. So relating back to that bug I said before, what if I told you that a bug in the Ruby virtual machine once made the Puppet process peg CPU usage around, like, I think it was like 90% or something. And the reason why that happened is just because of a system call all the way down in a system library, a system call called sigprocmask, which is being called via another. So this system called set context and get context is used by the Ruby VM to implement its threading implementation. And this system call pair typically uses sigprocmask internally. And it's used primarily for threading and exception handling. But because of because set context and get context are calling sigprocmask under the covers, and it's doing it more often than necessary, it turns out that it makes Puppet basically unusable. And here's a quote from a bug report against Puppet. And the bug report says, the Puppet process spends 40 to 60% time in system time, which lengthens the time a single Puppet run takes from a few minutes to greater than 20 minutes. And so someone was unable to run Puppet against their infrastructure because of a bug in the Ruby virtual machine that occurred because of a bug in a system library, right? So it's just literally bugs all the way down, and unless you understand like how the system works at every single layer, debugging and fixing that's basically impossible. I actually wrote a fix for this bug, but that fix was never accepted by the Ruby VM upstream. So I published the bug fix on my blog, right? And a friend of mine working at a huge company told me that without copying and pasting code off of a blog post they found on the internet into their like company's infrastructure, they weren't able to run Puppet, right? And so that just doesn't make any sense. Like that's like completely crazy that people have to go and copy code off of some random guy's blog and put it in their infrastructure so they could run Puppet to configure their servers. And so is it a coincidence then that the people at Puppet wrote this on their blog? We're working on rebuilding our entire client-side technology stack so it takes fewer resources, runs faster, and is more maintainable. And they're supposedly rebuilding some or all of their client-side stuff in C++ now as a result. I'm not saying those two things are directly related, but I think there's like an interesting correlation there that people had to copy and paste code off of potentially my blog to get Puppet to run, and now the Puppet people are rewriting everything in C++ instead of Ruby. And I'm not here to like just make fun of Puppet, right? Like the same bugs also affect Chef. So here's an interesting bug in Chef, right? So a bug, ohi 330. The bug title is ohi crashes on Solaris 11 or Ubuntu 12.04 in this particular Ruby thing, right? And what's actually happening when Chef is crashing here is it's crashing because of the garbage collection bug I mentioned earlier, that your Chef code is running, it's creating all these objects, right? The Ruby VM runs to do a garbage collection run, and the Ruby VM thinks that, hey, this object's no longer needed, I'm going to free it. It frees the object, but Chef is not done using it yet. And so Chef runs, and then Chef seg faults and explodes, and you're not able to configure any of your server resources because Chef wasn't able to get past a bug in the Ruby VM, right? And there's literally nothing you can do about that. Like if the Ruby VM is broken and you can't run Chef, how do you deploy new servers, right? You can't. And so the workaround in Chef was that they just disable the garbage collector, run the code that needs to run, and then re-enable the garbage collector after. And I think this is like a pretty insane, this is like a pretty like amazing thing for me, that like the fix for this bug is to literally disable part of the programming language, right? Like I feel like that says something about like the quality of the software, that like all of us are depending our infrastructure upon. Or like your infrastructure only, like it's really interesting to say that like I can only deploy new servers if I first disable the garbage collector. Right? It just doesn't make any sense to me. Like it's just completely nuts. So similarly, what if I told you that it's impossible to install a program securely on most versions of Linux? Probably someone would stand up and start screaming like, oh, but package managers have support for GPG. And my response to you would be no. And I'll explain why. And I'm going to talk about both Yum and apt because neither of them actually work properly. So Yum and GPG, it's like a really, really sad story. So the short version of the story is that GPG just doesn't work most of the time, and it's basically impossible to get it working properly. And I'm going to tell you a bunch of stories about that. So when you're using Yum and you're trying to get GPG working, there's a package called pygpgme. And this particular package is required on CentOS or Red Hat or other RPM-based systems. And what this package does is it goes and it verifies GPG signatures of packages you install via Yum. It turns out that on CentOS and Red Hat Linux 5 and early versions of CentOS 6 or Red Hat Linux 6, pygpgme is not listed as a dependency of Yum. So you can end up in a situation where you have Yum installed and you want to install packages that have GPG signatures on them, but you don't have this installed. And what happens in that case is that Yum just fails open, and it just doesn't tell you, like, hey, I couldn't verify the signature. It just installs the package for you and just doesn't bother verifying the signature. So you see lots of people talk about, like, hey, you should verify your GPG signatures, import the GPG key. Like, that's all well and good. Like, you can import a GPG key. You can set your config to verify GPG signatures. But if you don't have this installed, Yum won't verify signatures, and it won't tell you that it didn't do it. And I've like literally, and I've seen lots of people distribute software, like lots of companies are like, hey, download my software, here's a Yum repository. But I've never seen anyone ever mention you need to install pygpgme. And this is because, just a bug in the setup of the system, right? There's not many people know about it, and if you don't know about it, you're not verifying GPG signatures. So it doesn't matter. Like, you can sign the packages all you want, but if you don't have this installed, nothing's getting verified. Another sort of interesting configuration option is this configuration option, repo GPG check. So it turns out that there's like multiple layers of GPG signatures in Yum repositories and also in apt repositories, which I'll get to later. But in Yum repositories, most people don't actually understand how GPG works when it comes to package repositories. So there's two layers of GPG signatures. First, there's a signature on the repository itself, and then there's a lower level signature on each of the individual packages. These are separate signatures, and they have separate configuration options, and they work differently. So if you want to enable the GPG verification of the entire repository, you need to turn on repo GPG check. And that's separate from another option that people use that just, there's an option just called GPG check, and that has to do with the packages themselves. But repo GPG check is the check for the repository as a whole. And then to complicate matters even more, if you want to GPG sign your RPM packages, there's different versions of GPG signatures you can use. And there's this whole like really crazy bug around GPG v3 signatures, where if you sign an RPM with GPG version 3, and then you try to verify it on a newer system, newer systems aren't able to verify signatures made on previous GPG versions, unless you copy and paste like this blob into your RPM macros file to run every time you generate an RPM file. And this is like not documented really anywhere except for like this talk and maybe a blog post somewhere, right? And there's just like there's no way you can expect people to know all this stuff to just like correctly GPG sign their packages. And it gets worse. There's also an option in the Yum configuration called SSL verify. It turns out that SSL verify is defaulted to disabled on like CentOS I think 5 and 6. I believe in CentOS 7 they switched it to enabled, but this just means, right, that if you're planning on installing packages from a Yum repository server that you're connecting to over SSL, the certificates won't be verified unless you explicitly set this to true. So I recommend that you set that to true because it's a useful thing to turn on. But it's not just Yum that's a total horror show. It's also apt is a horror show. So the same story with apt. It just doesn't work most of the time, and it's basically impossible to get it working as well. So my first story for apt is there's two programs you can use to GPG sign Debian packages. The first program is called debsigs, and the second program is dpackagesig. And the two programs sign packages differently, and neither of them can verify the signatures that are produced by the other one. So you need to you need to basically figure out which one you actually want to use. But the amazing thing about signing Debian packages is that it's completely pointless because no Debian-based operating system verifies package signatures. So Debian and Ubuntu only verify GPG signatures of the repository itself, not of the individual packages. So even if you sit there and you figure out how to use debsigs or dpackagesig, it doesn't matter because those signatures are never being verified anyway. The only way to actually get package signatures to be verified is to create a massive XML policy document, which looks like this and lives at like a really weird place in the file system. It took me a long time to figure out how to construct one of these because this is actually not really documented anywhere because no one uses Debian package signatures. People think that like Debian verifies package signatures, but it doesn't. It only verifies package signatures if you've actually sat down and typed out an XML policy document like this. And by the way, if you're going to try to create a document like this, you have to make sure that it's named in a really specific way. It has to have the GPG key ID as a directory. Not as the file name. The file name can be anything you want, as long as the GPG key ID is in the directory. It just doesn't make any sense why this is structured the way it is, but this is how it is. And I've literally never seen anyone, like I've seen lots of people say, hey, install our GPG signed Debian package, but I've never seen anyone say, okay, if you want to actually verify the signature, you need to create an XML document that looks like this. And the reason why no one uses this is because no one knows that this exists or how to use it or how you're supposed to use it, right? There's just no documentation. And by the way, if that wasn't enough, both systems are vulnerable to replay attacks. Neither system deals with key revocation, and there's several other GPG-related attacks that both apt and yum are vulnerable to. So both of these systems are horribly, horribly broken. There's a really interesting paper written by, and I'm going to get into this paper again a little bit later when I talk about like a really scary attack. But there's a paper written by a bunch of researchers. I believe they're out of the University of Wisconsin. And the name of the paper is A Look in the Mirror, Attacks on Package Managers. And they sort of go through lots and lots of different security attacks against package managers, involving replay attacks or denial of service attacks. There's a lot of really interesting attacks. And I'm going to talk about a few of these in a few slides. But first, a really interesting bug. So what if I told you that the CA certificate bundle that you use accidentally revoked Amazon's SSL CA? So before I explain how this happened, I just want to give you a periodic reminder that all of your CA certificate bundles come from this URL. They all come from curl.hacks.se. So that makes me feel like really safe at night when I download my CA bundle from these people. But anyway, so there is a VM that was made by some of the folks at Chef. This VM is called opscode CentOS 511. And it was made sometime around 2015. And it updated the CA certificate bundle that comes with it that includes all the root certificates that you use to verify SSL certificates. And it turned out that when they were making this VM, they reran a script to pull the new certificates off of curl.hacks.se. And curl.hacks.se had accidentally revoked AWS's CA. And so what ended up happening was that if you were trying to connect to S3 or EC2 or any other AWS service, you no longer could if you had updated your bundled CA certificates. And the people at curl had this to say. They said, we in the curl project didn't anticipate anything of this. We get our data from Mozilla, and they changed the properties. We ran the same script every day for a long time, and one day the output changed. Sorry. And the result is that like accessing S3 from any vagrant boxes produced by Bento stopped working, or anyone who had happened to run the script at that exact moment who pulled in a set of certificates that's now broken can no longer connect to S3 or EC2 or whatever. So if you're potentially trying to connect to EC2 to deploy a bunch of infrastructure, you can't because SSL was broken. There's a full sort of workup of this bug and how I debugged it on the Chef blog, so if you want to check it out, the URL is in the talk. And by the way, PS, debugging SSL is really, really, really difficult to do. It was really, really painful to figure out the cause of that bug when I sat down to do it. And by the way, sort of a quick thing before I get into more bugs, like there's this idea in cognitive science about cognitive load, right? And so what is cognitive load? And I think this is like an important concept when you're thinking about like all these crazy bugs that I'm going through. What is cognitive load? Well, cognitive load refers to the total amount of effort you need to use in your brain to keep everything in, to keep all the data about what's going on in your working memory. And I guess why I mentioned cognitive load is that like you start to think like, at what point, when does all of these problems in our infrastructure and in our software systems become too much for us to remember just to get useful work done every day? I feel like, as we build, bigger systems using more, layers of abstraction, we have to remember more things that can go wrong at every layer of the stack, and it just becomes, it gets to the point where you're remembering so much stuff just to get like a little bit of work done every day. And I feel like, a common refrain that I hear from people in the software community is, oh, this isn't that hard, just read the code, right? So like, just read the code is impossible because you need to read millions of lines of code, right? That's what I was, sort of talking about earlier with when you're using Chef, you're getting all these crazy Chef bugs, and people say, oh, Chef's not working, just read the code. Well, I have to read all the code of Chef, all the code of the Chef dependencies, all the code of the Ruby VM, all the code of Linux, all the code of Linux kernel, all the code of my device drivers. Like at that point, I've already died because it took me 100 years to read all that code, right? And reading all the code is impossible, right? Like, and so on the whole idea of cognitive load, so a friend of mine who works at a huge company told me that people changing our Chef recipes to make something work for them, but then breaking everyone else's stuff is constant at our company right now. And I think that this has a lot to do with just like, again, like this idea that like to make a small change in your infrastructure, there's all these things that can go wrong like on your infrastructure stack and on your software stack, but also all these things that can go wrong like across from you. Like the person sitting next to you who's also working on their infrastructure might be changing stuff at the same time you're changing stuff, and both of your changes are blowing things up. And sort of, why things are the way they are, I don't know, but, I have some ideas around this, and this is part of a different talk called The Effect of Capitalism on Computing, but I'm not talking about that today. Anyway, so another interesting attack on package managers, to go back to bugs. So, like, what if I told you that you can do a denial of service attack against the computer just using yum and apt metadata? You would probably call me crazy, but it turns out that the researchers documented this, that if you just run, apt-get update or, yum update, and you reply with a never-ending file, yum and apt will happily fill the entire hard drive of the machine running yum update and bring the machine down. So, it's not really good software. And you might think, okay, well, who's going to do that, right? Like, who's going to point their computer at me and run, apt-get update or yum update and download a, 100 terabyte file and DOS their own machine? Like, I'm not an official mirror of Ubuntu. I'm not an official mirror of Fedora. Like, how likely is this attack really, right? I'm not an official mirror of lol, right? Well, it turns out that the academic paper I was studying before tried this attack, right? They were able to create a fake server. They, set up a bunch of fake packages. They emailed a bunch of the major Linux distributions, and they told them, hey, we have an official mirror. We're willing to give away bandwidth. Tell all of your users to point their machines at us and get their packages from us. And the quote from the paper is that Debian and CentOS listed the mirror within a few hours, and Fedora listed the fake mirror within minutes. Right? So you can easily set up a completely fraudulent package repository mirror, quote unquote mirror of an official distribution, and tell the major distributions, hey, tell your users to use this, right? And they're adding these things with no verification whatsoever, right? So you could have gone through and Trojan horsed every single package, in Fedora, and then gotten Fedora to add that as an official mirror, and then it doesn't even matter, right? Like, you can then go through and GPG sign these packages all you want. It just doesn't matter because they've all been Trojaned, and you're installing them without even realizing it, right? And there's a lot of other really, really crazy attacks like this in this paper. And again, the name of the paper is A Look in the Mirror, Attacks on Package Managers. So if you're interested in this sort of thing, you should check out this paper. It's really, really interesting, all the attacks that they found. Okay, so we've talked about attacks in the actual package management clients themselves, right? So hopefully you're thoroughly convinced that neither apt or yum actually work. So what about the tools that you use to generate package repositories themselves? Like, what if you're just, hey, I'm just someone hosting a bunch of Debian packages for my customers, or I'm just someone hosting a bunch of RPM packages for my customers. You probably use a tool called create repo. It turns out that create repo actually generates incorrect metadata sometimes. And I found this bug. This is related to a bug again in another library, further down the stack, called RPM utils. It turns out that RPM utils uses a find method instead of rfind when splitting version strings. So when create repo goes to split the version string off of the package, it parses the version string in the wrong direction. And this ends up becoming a problem because it ends up parsing the versions. It parses version strings that have 2 dashes in them in the wrong spot, right? So it will split them on the first dash when it's supposed to be splitting them on the second dash. And the result is you have incorrect package metadata. And you might say, who cares, right? You're splitting it on the wrong dash, big deal. Well, if you're trying to get people to actually upgrade to a newer version of a package later, you might want them to have the correct version in the repository metadata. And it turns out that this bug, like I actually wrote a script that could go and detect this. It turns out this is actually live on the official CentOS 7 mirrors right now. So there's like a set of packages, I think it's like maybe like 100 packages or something like that, that all have incorrect version numbers in them. So if anyone releases an update to these things and you want to like update to the latest version, it's possible that that's going to fail because Yum won't be able to do a version comparison because the version stored in the metadata on the server is just wrong. I filed a bug about this, but basically from what everyone was, what the open source folks at Red Hat were saying is that they don't actually care, so it's not going to get fixed. But so this is live on CentOS 7, the official repository now. Okay, so these are all cool stories. Or I hope you agree they're cool stories. But you might be thinking like, okay, what gives, right? Like, people are using infrastructure as code today, right now, though, right? Like, probably many of you are using like Chef and Puppet like right now to deploy like lots of servers. So like, how can all this other stuff be true if like people are using these tools today to get work done? And I would argue that like, indeed, right, people are using these things, but potentially with varying levels of success, and in many cases, great pain, right? So like I mentioned before, my friend who works at a huge company talking about how, yeah, we're using Chef, but every time we use it, we're just breaking each other's code, and it's like a huge pain, and like it's really, really difficult for us to get work done. I think that that's sort of a story I've heard from a lot of people, that, yeah, they're using these tools, but it's just as painful as, it's a different type of pain, right? Before you were using these tools, everyone had pain, dealing with a pile of bash scripts. And the promise was, hey, if you stop using bash scripts, you start using Chef or Puppet, all of your pain from bash scripts goes away. My argument is that the pain that you have from bash scripts now just gets pushed into pain that you have to experience around Ruby, around Chef, around Puppet, around all those other tools, right? So it's the same amount of pain, it's just the pain is like in a different area. So I don't know, in my opinion, and this is the end of my talk, and then you can ask me questions or yell at me if you don't agree, but in my opinion, I don't think we'll be able to have truly reproducible infrastructure until we figure out better ways of building computer systems. And I think this is like sort of part of ongoing research, right? Like, it's going to take time for people to figure out how to build better computer systems, and when we do that, we'll be able to have better ways of building reproducible infrastructure. My other opinion is that every time you move to a higher level of abstraction, you need to know more stuff, right? So as you move up to like Chef and Puppet, you now need to know like how to write Ruby, you need to know about all the bugs in Ruby, and then like all the bugs and everything below you. So as you add more layers, you need to know about more bugs. That's just the truth, right? You can't get away from that. And so maybe cutting out some layers of abstraction can sort of make problems like these more easily solvable. I don't really know, but that's just, again, another opinion. Opinion 3, like I think that, we probably need to be more honest and responsible about our choices and analysis of technology. You can find lots of talks where people rave about how dope or how awesome, Chef or Puppet or other infrastructure tool or like, other tools too. Like I didn't talk about things like SaltStack or Ansible or whatever, but I'm sure that those tools have the same sorts of problems. And you see lots of talks about people raving about how amazing these tools are. I think that we need to be more honest with each other that like, hey, these tools are probably cool in a lot of ways, but like they also have drawbacks too. And I think that analyzing these drawbacks and talking about them is important. This is probably the most unpopular opinion I'm going to have, is that there are huge companies making billions of dollars on top of these software systems, and I think it's the responsibility of a lot of these companies to invest in these systems and make them better, right? Like there's companies making billions of dollars from Yum or from apps by distributing their enterprise software through them, and I think like these companies need to be investing in making these tools like more secure, so we can guarantee that like people are actually installing the software they think they're installing. And my last opinion is that I don't think we've found the answer to infrastructure as code yet. Like I think what we have today is definitely better than what we had a few years ago. But I think that we need to keep going and build better systems if we want to make this problem more manageable. So anyway, that's it. It was a little short, but I'm happy to take any questions if anyone has any questions.
Hello, thank you for your talk. How could you define a better system? It has less layers of abstractions or something like that?
Yeah, I mean, so the question was, how do you define a better system? I think that's a good question. In my opinion, I think like a better system would be a system where when failures occur, it would be easier to understand exactly what's going on, right? Like, so the example I gave before about about there was like a fix for Chef where they just disable the garbage collector and then they run their code, right? Like that fix itself probably took the folks at Chef who were working on that weeks to understand like what the problem was and how to fix it. So I think like part of it is like when failures do occur in the layers below you, that those failures occur in a way that the layers above you can actually understand what's going on, right? Like so when I talked about the MySQL bug, right? So MySQL was able to detect that, hey, these mutexes aren't atomic, but instead of like destroying all your data, I'm going to let you know that, hey, there's probably a hardware problem, so that anything built on top of MySQL, if you're looking at the MySQL logs, you know, hey, something really weird is happening. There's possibly a hardware problem. So I don't know. I think that there's like stuff like that you can do at the lower layers, especially in like the language runtimes, to say like, hey, this is potentially a bug in the language runtime, and that could make it easier for people who are building complex software stacks above them, like to be able to debug and fix problems like that.
Oh, okay, thank you. And second question, why doesn't your patch was accepted?
Why wasn't the patch accepted? The Ruby project is sort of like a really complex political. I don't know. Not sure what the right word is. It's sort of a complex political scene where there's a lot of they've gotten better over the years, but at that time it was really, really difficult to get a patch accepted. I don't know why, but that's just the way it was. So.
Hello.
Hi.
Thanks for your talk. Should we continue use T for Pipit after knowing all of this?
Yeah, I mean, I don't know. It's up to you, right? It's up to like you have to make a business decision. So anyone who didn't hear the question was, should we keep using Chef and Puppet after all of this? I guess the question is like, should you keep using Linux after all this, right? Because you can't even install a package without like potentially getting rooted by by like a bunch of academics who created a fake server somewhere. Yeah, I don't know, right? Like I think that like that's a business decision. You have to decide, is it worth it to us to potentially rip all this out and rewrite it all in something else? And I would argue that like I don't know, it just depends on it's a business decision. I can't really say. I don't know for your business specifically, but I mean for my business we still use Chef. We definitely have a lot of pain when we use it, but we don't really have a choice because we just don't have like for us reinvesting and like ripping all that stuff out and rewriting it in another language would just take too much time and effort at this point. Like we're already invested, so we have to live with it for now. I think like another question might be right like along the same lines of that is like. Now that we know these problems exist, like how do we get the open source projects to actually fix these, right? Like how do we actually get like the Yum and app people to build better versions of Yum and app so that we can actually securely install programs? And I don't know the answer to that question, right? Like I think part of that is like raising awareness, right? And so I hope that like by giving talks like this and telling people like, hey, like there's all these attacks against package management and you can't install a package securely, hopefully like that'll raise awareness about these problems and maybe the Linux distributions will actually fix them.
Hello.
Hi.
I was just wondering, by your definition, you're saying that infrastructure as code is virtually impossible.
Mm-hmm.
But would you say that by the same definition that any code is virtually impossible? Like even writing an assembly, that would mean you would at least have to read the manual for the processor, for the CPU you're developing for. And then, it goes down to whatever depth of, insanity.
Yeah. That's a good question. I mean, so I would say that like that writing code in assembly and C is definitely very, very difficult. The only reason why I wouldn't say it's impossible is just because it's been around for so long, right? Like you're talking about like people have been writing kernels and operating systems for a really long time. And so a lot of the problems with like, x86 hardware is well understood at this point. And like the failure conditions are much more well understood than the Ruby garbage collector seg faulting when an object is freed when it's actually still in use. So I don't know. I think it's just sort of a function of like how long these things have been around and how long they've been known about, and that sort of helps disseminate knowledge, right? Like I don't know. I mean, it's a good question. It's a good question. I don't know. Sorry, I don't have a better answer.
Okay, thank you for your clear vision. And you have mentioned different language, for example, Bash, Ruby, and so on, but didn't mention, for example, Python. Is the same trouble, or you have some purpose?
Yeah. So the Python VM, I haven't really had a chance to look at the Python VM in detail, but I guess the point that I was making about high-level languages in general is that there's probably similar, so Ruby has all these problems with the garbage collector and the object allocator and everything, and I'm sure that Python has a similar set of bugs as well. And the point that I'm trying to make is essentially that whenever you write anything, even in Python, right? Like if you're using like Ansible or something like that is Python, right? Like when you're writing a bunch of code for Ansible, like you're still pulling in all the Python ecosystem and the Python toolchain to write infrastructure code. And so any bug in any of that ecosystem is going to cause problems for you. The same way that pulling in libraries in Ruby could potentially cause problems for you when you're writing code in Chef. The only reason I didn't mention Python specifically is just because the two biggest tools, Chef and Puppet, are Ruby-based tools right now. But I'm sure there's sort of a similar set of problems around Python and Python-related tools. But sorry, I don't have a better example for you on that.
I have a next question. In big projects, we have some unit tests, maybe integration tests. When you talk about infrastructure as code, there is no unit test and integration test. Could be these problems fixed with properly coding?
Yeah. Yeah, no, that's a good question. Asking about like unit tests and infrastructure code. So there's a few things that people use for infrastructure tests. There's a project called Kitchen, which allows people to run their Chef recipes in like a VM and actually write tests against them, like unit style tests. There's also a similar project for Puppet I think it's called Beaker, that you can use that'll let you run your Puppet manifests in a testing environment and like assert things about the Puppet manifests. So there are some like testing things that exist. The problem with like garbage collector bugs, like the one I mentioned earlier, is that like bugs like that only trigger at like really specific times when a certain amount of memory has been allocated or when a process has been running a certain length of time. And it's just really, really hard to reproduce those in a testing environment. I mean, sometimes you can and sometimes you can't. It's just sort of hit or miss. But yeah, I mean, I agree with you that if people wrote some unit tests or some integration tests for their infrastructure, that would probably help a bit. And so I definitely would recommend that if you can or you have like the engineering budget to do so, writing tests with like Kitchen or Beaker or some other system will definitely help like reduce the number of bugs you have to deal with when you deploy your Chef and Puppet stuff to production.
Hello, thank you for the great talk.
Thanks.
Do you think ANB or some other secret services are using these vulnerabilities in their research of spying on Linux users?
I don't know, but I'll say this, right? If a bunch of people at just like a research university can figure out like these attacks, then I'm sure that like people who are trained in sort of the stuff that you're talking about probably knew about these attacks a long time ago. I mean, I don't know. I would definitely, like, if you ask me would I bet on that, I would definitely bet on that for sure. I don't know if there's any evidence of that, though.
Hello.
Hi.
Thank you for your talk. I have a question. What do you think about Docker and all these things about packaging in Docker?
Yeah, so I have like sort of a really weird opinion about Docker. So I used to work I used to work at VMware on the ESX kernel, so I used to actually work on virtualization stuff. And my experience, and again, this is just like my opinion, and this could be totally different from anything you all think, but my opinion on that is that you're basically taking the most complicated and difficult to understand part of the software stack, right, and you're inserting additional code there, which means you're adding a lot more code to a part of the computing system that people understand the least. And so that comes with trade-offs, again, like anything else, right? Like, containerization is really cool in a lot of ways, but in a lot of ways, right, it makes things harder to debug, right? Like you're trying to debug a problem with containers, now you have additional container code to debug, and like maybe that's a problem for you, maybe it's not. I don't know. I know a lot of folks, at least a lot of people that I know at companies in San Francisco. There's sort of like this interesting meme right now where like a lot of people are using containers like in development and in testing, but very few people are actually using containers in production. And I don't know why that. I don't know necessarily why that is, but I think part of that could just be that you're inserting a lot of code to a part of the system that people don't really understand as well as the other. Again, it's just adding additional layers of abstraction means you now have to understand how more things work. So I don't know. I mean, I think it can be good or it can be bad.
No more questions? Thank
All
you
right,
very
thanks.
much.
Yeah, bye.
We'll have a break for 1 hour and we'll return with CSRF issues. in 2 o'clock.